Well, as I'm getting ready to make this video, it is supposed to be nicer outside, but it is snowing and sleeting and all sorts of nonsense. And I'll tell you what, I'm getting sick of the winter. So tried to spice it up tonight with some warm summery feelings. We've got our sun cooking here on the left, and we're filling up our swimming pool here in the upper right-hand corner. And it kind of leads into our topic tonight. We're going to work on writing some accumulation functions. And I think this is a very special talent that seems to be one of those difference makers between getting a 4 and a 5 on the AP exam. The ability to not only write but also feel comfortable with manipulating these functions and taking their derivatives and so forth. So our first scenario here tonight, I want to pose this idea. Water is pouring into a swimming pool at a rate represented by P of T. Now, I didn't want to burden you with an actual function. I didn't want to, I'm not trying to clutter this up more than it already is. I'm not worried about who P of T actually is. We're just saying it's a function that represents the rate at which the water is pouring into the swimming pool. Meanwhile, simultaneously, water is leaking out at a rate represented by L of T. Both of these functions are measured in gallons per minute. Notice the word per here also illustrates that we're talking about rates. Initially, the pool contains 800 gallons of water, and the word initially is implying that at the moment when T equals 0, there are 800 gallons of water. Now, the ultimate question I want to tackle is here in blue, and it says write a function A of T that represents the amount of water in the tank at any time T. Now, before we actually tackle that one, though, perhaps it's going to be helpful if we ask ourselves, could I find the amount of water in the pool specifically at something like T? Whoa. It's getting out of control. All right, sliding back over. What if I wanted to know how much is in the pool at the moment when T equals 6 specifically? So instead of being real general about it, let's be real specific here. And how would we find out how much water is in the pool at T equals 6? Well, the first thing I would do is I would say, well, I know I've got 800 to begin with. On top of that number, I would add the integral from 0 to 6 of P of T dt. And then from that total, I would then subtract the integral from 0 to 6 of L of T dt. So I'm calculating the amount that has entered during that time span. I'm then calculating the amount that has leaked out during that time span. And we're putting it all together to get a total amount at T equals 6. So thinking about that process, I hope it's going to springboard us into this next idea of tackling this A of T function. Can we write a function for A of T? All right. A of T is, again, we're going to start with our base amount, 800. Always consider the fact that the pool is not empty when we started. Now on top of that, I'm going to add the integral from 0 to T, and here's where it gets interesting, of P of X dx. Now, quite frankly, the reason we can't use the same variable there is maybe after we write this function, we wanted to use it to calculate, how much water's in the pool at, say, A equals 2. This notation here says I'm going to substitute a 2 in for every single T that I see, and, I want to get to this part here, and I want to integrate from 0 to 2 without plugging a 2 into this P function. And as long as these variables are different, we won't accidentally plug the 2 in for the P function, okay? We also want to then subtract the amount of water that is leaked out during this time span. And again, it's going to be L of X dx. So right there you have it. We could trim this function up a little bit and combine the two integrals into one. So that's what I'm going to do right here. I'm going to say A of T is really 800 plus the integral from 0 to T, P of X minus L of X with respect to X, okay? And that does it for that function. Now, where that's going to be really useful is there's a variety of questions. They'll probably ask you, hey, at what moment is the pool, filling the fastest or so forth and so forth. And it's very common that you need to then take the derivative of this function. And the derivative here, the 800 is going to now be dead because of the derivative of a constant. We're then going to use our second fundamental theorem here on this portion where we take the upper bound and we substitute it into P and L. And so if they ever asked you, hey, when's the amount of water in the pool, at its highest or lowest point, you would set this derivative equal to 0. And basically whenever P equals L, you have a critical point. Whenever P's greater than L, we would say that the amount of water in the pool is increasing, and whenever P of T is less than L of T, we'd say the amount of the water is decreasing. So there you have it. All right, our next example today is a real wordy one, and as we go through our Good Morning Math problems, we're going to get more and more current with these problems, and I think you're going to see a trend, a very dangerous trend, and that's you're going to see these problems get wordier and wordier. So the one that we have in front of you is a fairly recent one, and it's significantly wordier than some of the ones we've been doing recently. And notice that I haven't even included parts C and D. But anyway, I want you to imagine oil, unfortunately, leaking from a pipeline onto the surface of a lake, and it's forming an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil slick takes on the form of a right circular cylinder with both its radius and height changing. Now, this is a tough one to visualize, but I think it's going to be a very wide and short right circular cylinder. It's going to have a very large radius with a very small height, is what I'm picturing anyway. Now, part A, I'm not going to solve part A here in the video tonight. At some point here, I need you to hit the pause button, and I want to see you solve part A completely on your own. And this will be one of the things that I check tomorrow in your notebook. So, put a little note here, or you can do it right now and get it out of the way. We need to solve this on your own, and we'll check in your notebook tomorrow. You hear that, Ben? All right, now, part B, let's tackle that one. It says a recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is represented by this nice R of T function. T is the time in minutes since the device began working, and oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time when the oil slick reaches its maximum volume. Now, you'll notice here, at no part did they actually say write an accumulation function, and they typically won't. I think it's going to be the student's responsibility here to recognize the need for one, and I'm going to say that A of T, the amount of oil in the slick, is equal to. Now, they never told me what the initial amount was. They didn't tell me how much time had elapsed until the recovery device arrived. So what I'm going to do is I'm going to put A sub 0. And what that is that's going to represent my initial amount of oil. I don't know it. And then on top of that, I'm going to add from 0 to T. 0 represents the time when the device arrived. The 2,000 gallons that's being added to the slick minus R of T. Whoops. Did you catch that mistake? This cannot be a T. That has to be an X. Okay, and then a dx. So now they said, okay, when does this oil slick reach its maximum volume? So that's like maximum amount, right? A prime. What's going to happen is the initial amount is now dead, and that's one of the reasons they didn't need to tell us that. Now the 2,000 is not dead because the 2,000 is tucked inside the integrand, okay? And I'm going to substitute this t in for the x, and I've got the derivative e is equal to 2,000 minus r of t, which of course is 400 radical t. We're going to set that bar equal to 0. So I've got 2,000 equals 400 radical t. Divide the 400 over, square both sides. And we've got 25 equals t as our critical point. Now we need to prove that that's a maximizing moment, not a minimizing. So there's t equals 0, here's t equals 25. And I'm going to substitute smart values into A prime. What I mean by smart values here, I'm going to plug a 1 in. And let's see. So I'm really thinking, I want you to picture 400 radical t right here. And if I plug a 1 in, 2,000 minus 400 is definitely positive. Okay, and then what's bigger than 25 that would be a smart number? I actually picked 36. Square root of 36 is 6. 400 times 6 is 2,400. And 2,000 minus 2,400 is a negative number. So now we could say, what does that tell me about A? It tells me A is increasing, A is decreasing, and the amount of oil in that slick is going to reach its maximum point at T equals 25. So don't forget to solve part A on your own, and I look forward to seeing your answer tomorrow. Let's go get one more example while we're at it. This is one of my favorite problems, and certainly as I look out my window and see it snowing, I could certainly visualize this problem happening here. But it says there's no snow on Janet's driveway right now when snow begins to fall at midnight. And then from midnight to 9 a.m., snow accumulates on her driveway at a rate modeled by f of t, measured in cubic feet per hour, where t is measured in hours since midnight. Janet starts removing snow at 6 a.m. in order to get to Good Morning Math on time. The rate, g of t, in cubic feet per hour at which Janet removes the snow in her driveway is given by the following piecewise function. Now, here's what I want you to do. I'm going to tweak this just a little bit. All right? I want us to pretend, hey, let's pretend there was some snow in there. All right? Let's scribble this out. Let's say that at midnight, how much should we say? Let's say there was 10 cubic feet of snow already in her driveway at midnight, okay? And midnight represents t equals 0, of course. I want you guys to write an accumulation function to represent the amount of snow at any time t sitting in her driveway. Okay, and this will be the second thing that I check as I come around and look at your notebook tomorrow. So there's two things. We had to finish part A on the last one with the oil slick. Then I want you to come in here and just write the accumulation function. You don't have to derive it. You don't have to manipulate it. You don't have to do anything else. I just want you to write a function that represents the amount of snow sitting in her driveway at any time t. Good luck. I'll see you tomorrow.